So our lecture today is going to be about NFA to DFA conversion. And again, let me remind you that in this course, we are not introducing the concepts of NFA and DFA and regular expressions. In my presentation, I assume that you already know them. You already know the basic concepts of NFAs, DFAs, and regular expressions. And if you don't know them, then you need to review your material, your 135 material. What we are doing here is that we are reviewing, to some extent, we are reviewing some of the material, but we are emphasizing the concepts that are used in building a compiler. So the concepts that are actually used in building a compiler are writing a regular expression to represent a part of speech in a programming language, like an identifier, as an integer number, a floating point number, comments, strings, etc. So we did this. We did some examples on this. Now, the next part is that we discussed last time, in fact, is converting the regular expression to an NFA. So that's something that we did last time by studying the Thompson construction that converts an NFA, a regular expression, to an NFA. Now it's time to study the conversion of an NFA to a DFA. And as we said in previous lectures, we would like to eventually convert to a DFA because the DFA can be programmed very easily. Now, NFA to DFA conversion. So this is something that we would like to understand very well in this course. So last time, what we did last time, in the last part of last lecture, we traced how an NFA works on an input string. So we said, OK, we'll have a start state. Then from the start state, you may have one or more possible transitions. So it could be one transition to another state, but it could be multiple transitions. So the question is, why do we have multiple transitions in NFAs? There are two reasons for that that lead to this, to multiple transitions from a given state. We are in a given state, and we are seeing a certain character in the input or a symbol, but there are multiple transitions in an NFA for two reasons. What's the first reason? So there are two different reasons that will lead to having multiple transitions in an NFA. Reason number one is that from a given state, you can have multiple transitions for the same symbol. In an NFA, you can have an A and another A. You can have this. So this can lead to multiple transitions. The second reason,
the empty string.
Yeah, the empty string, the epsilon. So you can have A and you can have A, but you can have epsilon. So if this is state N0, N1, N2, then if you are in N0 and you get an A, you see an A in the input, there are two possibilities. First possibility is going to N1. Second possibility, second option, is going to N1, then taking the epsilon transition to N2. So when you are in N0 and you get an A, there are two possibilities. The next state is going to be either N1 or N2. So that's why with the NFA, we say that when you are in N0, your next state is going to be the set N1, N2. So generally speaking, for an NFA, if you are in a given state and you see a certain symbol in the input, that symbol will take you to a set of other states. That set could have one state in it, it could have many states in it, and it could have 0 states in it, right? If you are here, if you are in this state, and the only transition that you have is a B, and you are seeing an A, you are in this state and you are getting an A in the input, then this means that you go to an empty state, no state, the phi state that we will call the state that corresponds to no state in the NFA. So now the point, the whole idea behind converting an NFA to a DFA is to think of each one of these combinations of states, combinations of NFA states or subsets of NFA states as a state. So we can say, OK, this set of N1 and N2, we can think of this as a DFA state. So we'll call it D1 or D2 or whatever. This is the whole idea behind this. OK. So now, having said that, let's apply it to this small example. We'll go through two examples to this. This is a simple example. Then we'll go through this example. OK, so let's start with this example. So now, since we have N1 and N2, now how many possible states can we have in the corresponding DFA? Because in the corresponding DFA, any combination or subset of states, subset of NFA states, will be viewed as a separate DFA state. So how many possible DFAs, how many possible DFA states can we have? 4. And these are, N1 by itself is a DFA state. We call it D1. N2 by itself is a DFA state. N1 and N2 together, we call them D3. And nothing, the empty set, we may call it D4. OK? So with 4 states, with 2 states in the NFA, we can have up to 4 states in the corresponding DFA. Now, what if we have 3 NFA states? N1, N2, and 3. How many DFA states can we possibly have? 8, which is 2 power 3. 8. Yeah. So for the DFA and the DFA, we'll have 2 power 3. And these are going to be, N1 by itself, N2 by itself, N3 by itself, N1 and N2, N1 and N3, N2 and N3, and all of them N1, N2, N3, and then nothing. So these are all the possible states. So in general, if you have n states in the NFA, if the NFA has n states, the corresponding DFA can have up to 2 power n states. And why 2 power n? Because this is the size of the power set. This here is the power set of this set. So this is a set. And the set of these sets is the power set. OK? This is the power set. This is the power set of this. The set of all possible subsets. And that's why the procedure that converts from an NFA to a DFA is called the subset construction. It's called subset construction. OK. So now let's do this in a naive way by just looking at all possible states. So in this case, I'm going to say, OK, I will have N1. I will have N2. I will have nothing. And I will have N1, 2. So this corresponds to N1 and N2. Or we can call it, for now, we can call it this, N1 and 2. OK. So now, the idea of this conversion is to look at all possible transitions. So if I am in N1 and I get an A, of course, here I'm assuming that sigma is AB. Clearly, sigma here is AB. If I'm in A1 and I get an A, the A will take me to N2. So there is no other possibility here if you get an A when you are in N1. Now, if you get a B when you are in N1, how many possibilities are there? Two possibilities. If you get a B, you can either stay in N1, or you can stay in N1, or you can stay in N1, then you take the epsilon transition to N2. So when you get a B, because of the epsilon transitions, you can either choose to stay in N1, or you can choose to take this cycle and stay in N1. Then you can take the epsilon transition to N2. So if you get a B when you are in N1, you will not go to N1 or N2. You will go to N1, N2. This is the set of states that we will think of as a single DFA state. Okay, so this is a key idea. Now, when we did this, when we do something like this, we may have multiple epsilon transitions. So for example, if you have something like this, state N1, then you have a B, and then you have an epsilon that takes you to N2, then an epsilon that takes you to N3, then an A that takes you to N4. But here you can have an epsilon that takes you to N5, and then a B that takes you to N6. Now here, if you get a B and you are in N1, what set of states are constitute the possible target for this? So if you are in N1 and you get a B, you can possibly go to N2, and you can take epsilon transitions to N3 and N5, but you cannot go to N4 or N6, right? Right. So if you get a B, you are in N1 and you get a B, you can go to N2, you can go to N3, you can go to N5, but you cannot go to N6. You cannot use another B, right? You got a single B. Yeah.
Could you also remain in N1?
Yes, and you can remain in N1. So in this case, the set of states that you can transition to is N1, N2, N3, N5. And this set is what we call the epsilon closure of N1. So basically, when you get a B, you go to N1, but then you'll have to look at the epsilon closure. This is the epsilon closure of N1. What's the epsilon closure of N1? The epsilon closure of N1 is N1 itself union all the states that you can reach from N1 via epsilon transitions. Okay? So the epsilon closure of N1 is a set that includes N1 itself and all the states that you can reach from N1 via epsilon transitions. By the way, thinking of this algorithmically, and think of this NFA as a graph. Which graph algorithm would you use to compute the epsilon closure for a state? Which graph algorithm would you use? This is a graph. So these are nodes and these are edges. Yes?
Depth first?
You can use any traversal. In fact, you can use depth first or breadth first, with the source being
N1?
Yeah, N1, the state that you are trying to compute the epsilon closure for. But in your traversal, there is an important condition in your traversal. What's that condition that you should satisfy in your traversal?
That it's traversing via an epsilon?
Exactly. So you only consider epsilons, and you ignore non-epsilon edges. So it's like constructing a graph that doesn't have any of these. We don't see these. We only see epsilons. when we are trying to construct the epsilon closure for a given state. Okay? All right, so this is the concept of the epsilon closure. Now here, basically when we get a B and we are in N1, we are looking at the epsilon closure of N1, which is N1, N2. So in our example, the epsilon closure of N1 equals the set N1, N2. Now if we are in N2 and we get an A, when we are in N2 and we get an A, what happens? You don't have any transition, so you go to a no state, which is the phi state, the set of no NFA states. So the set that corresponds to no states in the NFA is still a set in the DFA that we will be constructing. So if you are in N2 and you get an A, you go to this. Okay, and what's the epsilon closure of N2? What's the epsilon closure of N2?
Just N2.
N2 only, right? N2 by itself, because there are no epsilons, there are no outgoing edges with an epsilon out of N2. So the epsilon closure of N2 is N2 itself. The epsilon closure of N1 is N1 and N2. Okay? Now, this is for an A. If we are in N2 and we get a B, so in N2 you get a B, you go to N1, but you have to find the epsilon closure of this. So you have to trade, so you can also go to N2. So in fact, any state that has an outgoing epsilon and a transition, an epsilon transition out of it, it will never be a destination by itself, right? So in here, N1, if you are in N2 and you get a B, you go to N1, but you can take the epsilon transition to N2 again, so that takes you to N1, N2. So N2 with a B goes to N1, N2. Now we have to, of course, the epsilon, the transitions for the phi, if you are in phi, then you can only be in phi. And if you are in N1, N2, we have to compute the transitions. So now for N1, N2, the transitions out of N1, N2, we compute the transitions for N1, and we unite them with the transitions for N2. So we compute the union of, so it's like this, delta of N1, N2 equals delta of N1, which will give you a set of states union delta of N2 and some epsilon, some symbol. So okay, so let's use this notation, N12 and a symbol x. Delta of N12 and symbol x is delta of N1 symbol x union delta of N2 symbol x. So now what's delta N12 of an A? Delta N12 of an A, we look at what we get for an N1 with an A. N1 with an A takes us to N2, right? N2 on an A takes us to phi. So delta of N12 and A equals delta of N1 and A union delta of N2 and A. And this is delta of N1 and A, the transition function for N1 and A. This is going to give us N2. And this is what? N2 and A. What's delta N2 and A? It's phi. So N2 union phi, that's N2. Okay, so on an A, because here this means that I am either in N1 or in N2, but in either case, I can only go to I can only go to N2. So on an A, I can only go to N2. Now N12 on a B, so N1 with a B goes to N12, and N12 is just the state that has all states in it, so it can't get any bigger than this. So basically, if I'm in N12 and I get a B, where will I go? N12. So it's going to be N12 union something, N12 union anything is going to be N12. So with a B, I stay here. Okay? So now we have computed all the transitions. So what remains to complete the construction?
Final state.
Yeah, final. Which states are final? Any state that has an N1 in it. Because this is a final state, because it's N1 itself, but also any state that has an N1 in it will be a final state. Why? Because what this means is, it means that I am either an N1 or an N2. There are two possibilities, but one of these possibilities is an accept state. So this means that I'm in an accept state. Remember that in the NFA, if you can find one path that takes you from a start state to an accept state, then that's enough to accept a string. Okay. So these are the accept states. What's the start state? No, it's not going to be N1. Generally speaking, it's going to be the epsilon closure of N1. The epsilon closure of N1. And the epsilon closure of N1 is N1, N2. So this is the actual start state. Why? Because N1 is a state that you can never stay in it. There is an epsilon transition out of it. So N1 is an unstable state. You can't stay in it because of the epsilon transition. In fact, if you look at this DFA that we have constructed, if you look at N1, you'll see that N1 can be eliminated. Why?
You can't get because it has only outgoing.
Yeah, because it's not reachable. It only has outgoing edges. So N1 can be deleted, and we can get, the final DFA is going to be this. So you will start with, let's rewrite it in a clearer way. N1, N2. And if you get an A, you go to N2. And the B takes you back to N1, N2. And with the B, you stay in N1, N2, which is an accept state. And if you are in N2 and you get an A, you go to a trap state. And in the trap state, you stay there. Okay. So I want to make sure that this is a DFA. So for each state, there is a single transition for each symbol. So here is a B and an A. For N2, there is an A and a B. And for phi, there is A and B. So this is the state after we cleaned up the states that we did not, that are unreachable. Okay, so any questions on this? And then we can rename them. We can rename these states. So we can rename this to D0, and rename this to D1, and rename this to D2. And this is our DFA. So it's about, the whole thing is about renaming a set of NFA states to, or mapping a set of NFA states to one DFA state. So now, generally speaking, which will have more states in it, the DFA or the NFA?
The DFA.
The DFA can have up to an exponential function of the number of states in the NFA. So for example, in this example that we will start working on in a minute, this has 10 NFA states in it. So with 10 NFA states, we can have up to 2 power 10, and 2 power 10 is exactly 1024. So you should be wondering now how we are going to fit 1024 states on the board.
It's not that big.
Okay. So we're staying here over the weekend, drawing all of these 1,000 states. Yeah.
Now, we've been saying up to 2 to the n states. So in what situation would you max out? Would you have to use the maximum number of states?
Maybe it's hard to construct an example in which you will, you will use all of them. It has to be an artificial example, but in real and useful NFAs, you will only use a small subset of the possible states. So in this example, we'll see how many of these 1,000 states, how many of them will actually get used. So the algorithm that we have just described, it will just look at all possible states, and then it will eliminate the ones that are not reachable. This is what we have done. But now this will not work on this, because with this, if we were to do the same thing on this, we will have to draw 1024 states first and then eliminate the ones that will not be used. Well, a smarter way of doing this is only considering the states that are reachable. So you start from the start state and discover DFA states. So initially, you don't have any state discovered. In fact, your first state that you discover is the epsilon closure of your start state. So that's your first state. Then you will keep discovering states, as we will see. So you discover DFA states. The ones that you discover, you look at their transitions. The ones that you don't discover are the ones that are not reachable. So the ones that are not reachable, you will never reach them, and you will never have to worry about them, as we will see in a minute. So okay. So this is, so let's, we are done with this. So we will have this table. This has the DFA state. This is NFA states, the corresponding NFA states. And then we'll have the epsilon closure of the delta transition. So we're going to say the epsilon closure of delta of D. So the DFA state, this is what we will call D. Okay, of D and X. Now, how many X's do we have to worry about in this example? Sigma here is what? ABC. Our sigma here is ABC, so we'll have to worry about X equals A, X equals B, and X equals C. Okay. Now our seed state, the first state is going to be our D0, which will always be the epsilon closure of the start state. So the epsilon closure of N0 is what? N0 itself. So this is the first state that we first discovered. This is our seed. We start from the epsilon closure of the start state in the NFA. And this is, in this case, it's N0. Okay? Then for this, we will compute the transitions, and we will discover new states. So if we are in N0 and we get an A, where will that take us? So we'll have to take the epsilon closure of the answer. So if we are, if we just look at the delta of N0 and A, this is going to be N1. But the epsilon closure of delta of N0 and A is going to be a bigger set, because when you get to N1, now compute the epsilon closure. Run a DFS on N1 with the epsilon edges taken into account. So this will take you to, of course, N1 itself plus N2 plus N3 plus N4. Will it take you to N5? No. But it will take you to N6. Will it take you anywhere else?
N9.
Yes, N9, because you can take this epsilon to N9. OK? So you have 6 of them. So now this set of N1 states, we just call it our D1. So this is going to become our D1. And our D1 is this set of states, N1, N2, N3, N4, N6, and N9. So we have discovered this set of NFA states. We called it D1. And it's just a new state that we have discovered. And now our transition here on A is going to be D1. So I could have written this whole thing, but now that we named it D1, I will just call it D1. Now if I'm in N0 and I get a B, where will that take me? I'm in N0, so we're completing these transitions. I'm in N0 and I got a B. Nowhere. So that's a phi. I'm in N0 and I get a C.
Also.
Same thing. It's phi. OK? So in fact, this phi, it means that I have just discovered a phi state. So this phi is a subset of the states, a subset that has no set in it, no NFA set in it. So I just call it, it's a special state that I call D phi. OK, and it consists of nothing. The corresponding set of NFA states is the empty set. OK, now the point here in this procedure, the idea is that only the states that I discover, I look at their transitions, and they will lead to discovering other states and so on. So now this DFA state that I'm in, I will look at its possible transitions with an A. So let's, if we, this is going to take you to, let's N3, N4, N6, and N9.
Are we?
It's
Is it supposed to be a transition between 8 and 9?
Oh,
The epsilon.
yes. So that's an epsilon. Yeah, thank you for catching this. By the way, where does this NFA come from? In fact, we did it last time.
Oh, it's a,
So who remembers where this came from?
isn't it the A with the parentheses B union C?
Yeah. So this was the corresponding regular expression is A concatenated with B union C star. Okay. So we did this last time. So this is the NFA that we constructed for the regular expression A concatenated with B union C star. So the star is for the union. Okay. All right. So now we will have to find transitions for this D1. But D1 consists of 6 states. So if we are in any one of these and we get an A, where will this take us? If we are in this, we get an A, nowhere. If we are in this and get an A, nowhere. nowhere. So there are, if you look at all 6 of them, there is no transition on an A. So the A takes you nowhere. There is no A going out of these marked states. So if I get an A, I will go to phi. Now if I get a B, and I'm in one of these, and you get a B, where will you go? So if you are here, you go nowhere. So which one of these states that are marked in red has a B transition? Number 4. Yeah. So this is the only one that has a B transition. So this B transition will take me to N5. So I'm discovering a new state now that has N5 in it. Now, will I stop at N5? No, I have to do the Epsilon closure. So I have to take all possible Epsilon transitions. So I'm in N5, that can take me to N8. Then N8 can take me to N9. Okay? And N8 can take me back to N3. And N3 can take me to N4 and N6. Okay? So in this case, if I am in one of these states, N1, N2, and I get a B that can take me to, I will write it here. Here I will just write the name, which is, I will call it D2. So it can take me to N5, N8, N9, and this will take me back to N3, and N3 can take me to N4 and N6. Okay, is everyone following this? Okay, so now we discovered a new state. Of course, this state is different from this state. For example, N5 is here, but N5 is not here. N1 is here, is in D1, but it's not here. So there are different states. By the way, if you rediscover the same state, you don't create a new state. Okay, otherwise you'll never finish. So we discovered a new state, but we will continue this transition. So transition on B led to D2. Transition on C, it's very similar. So everything will be the same except
reach N7.
Yeah, so we will be reaching N7 instead of N5. Then everything else will be the same. So but it's a different state. So it's going to be a D3, and this D3 has N7, then everything else the same. Okay? And we will call it D3. Now, what should we do next? The transitions for D phi. So if it's an empty state, it has no transitions, so it's going to only go to phi or D phi. In fact, we should call this D phi to be consistent. D phi. So it's going to be D phi. So now, what should we do next? Look at the transitions for this D2. So D2 has, so let's mark the different states. So this is, D2 is N5, 8, 9, 3, 4, 6. And if we are in any one of these states and we get an A, where will that take us? Or in other words, is there an A transition out of any of these states? No. So it's going to be D phi. Okay. So this is going to be D phi for an A. Yeah, so let me just draw this to avoid. Okay. So it doesn't look like a nice table, but it's at least things are clearer now. So this is a d phi. And then with if we are in any one of these states and we get a b, where will that take us? So if you are here and you get a b.
And in 5, they can go N8, N3, or that way. Or
Okay.
N9.
Back to D2.
Mm-hmm. Yeah, so if you are in one of these, is N4, no, yeah, N4 is one of them. So if you get a B, that will take you to N5, and then N8, N9, so it's going to be the same, right? So if you are in any one of these states and you get a B, you stay there. And if you are in any one of these states and you get a C,
Same thing.
you stay there. So C takes you to N7, and then N7 takes you to the same states. So you're going to go to D3. Now, if you are in one of these states, if you are in, sorry, here we are in these states and we get a C. So if we are in these, yeah, so that will take us to D3. And if we are in any one of these states and we get an A, D phi again. If we are in any one of these states and we get a B, so what will happen? But this, if you are in one of these states, but they include N4, right? So N4 with the B will take you to N5. So where will this take you?
D2.
D2. Yeah. So if you are in any one of these states, the one that matters here is N4. If you are in N4 and you get a B, that will take you to N5. Then from N5 you get that epsilon closure that includes N8, N9, N3, N4, and N6. So that's going to take you on a B. That's going to take you to D2. And on a C, if you are in this and you get a C, again, the C will take you to, the N6 will take you to N7. Then the epsilon closure will take you to the rest of the states in D3. So you will get D3. So now the point is that we are not discovering new states. So we got lucky here that this D2 led to states that we have already discovered. We did not discover any new states. And this D3 led to states that we have already discovered. So when we stop discovering new states, we just stop. The algorithm terminates. So we only needed 5 states out of 1,024 states. Okay? So that's why we didn't have to draw 1,024 states on the board. Now to draw the DFA in this case, it's going to be straightforward. So you are in D0. So this is your DFA. This table here is going to be your DFA. If you are in D0, you get an A. You go to D1. If you get a B, you go to D phi. And if you get a C, you also go to D phi. So this is a B or a C. If you are in D1 and you get an A, if you are in D1 and you get an A, you go to D phi. In fact, if you are in D1 and you get a B, you go to D2. Okay, and when you are in D1 and you get a C, you go to D3. Then if you are in D phi, you are in D phi. A, B, C. If you are in D2 and you get an A, you go to D phi, and D3 you also go to D phi. Yeah, so these I'm going to make it messy. Yeah, in fact, in the book, they're doing the same example in the book, and they're not showing the d phi explicitly. So if you remove the d phi, it will you will get rid of all of this mess of these transitions to d phi. But in order for this to be an explicit DFA, you have to have transitions for all symbols. So D2 on a B, you stay in D2. With a C, you go to D3. And on D3, with a D2, with a B, you go to D2. And with a C, you stay in. Okay, so what's missing?
Final state.
Yeah, final state. So how do we identify the final states? The states that have N9 in them. So any state that has N9 in it.
1, 2, and 3.
Yeah. Okay, so the states that have N9 are final states. One, two, and three. And if you look at the, if you look at the original regular expression, this is really equivalent to the original regular expression, which is A union BC star, because with an A, if you only have an A, then it's an accept state. And if you start generating B's and C's, you can generate as many B's and C's as you want, because B's and C's take you between these two accept states. So you can keep looping with B's and C's. So it's A followed by as many B's and C's as you want. And this is the, so we went from regular expression to NFA, then to DFA. And the point here is that we have this procedure that avoids enumerating all possible states. It only cares about the states that get discovered, that are reachable. So it starts from a start state, which is the epsilon closure of the start state in the original NFA. And that's our seed. That's the state that we start with. And from that state, we look at the transitions, and those transitions lead to discovering other states. And whenever we discover a state, we look at its transitions. And we stop when we don't discover any new states. Okay? So this is the subset construction for converting an NFA into a DFA. Any questions on this? Okay, so in fact, we ran out of time, so we don't have time to write some pseudocode for this subset construction. So next time we will write the pseudocode